Hi, today we're going to be investigating pendulum motion. Specifically, we're going to be looking at the equation that's displayed on the screen right now. T equals 2 pi into the square root of the length of the pendulum, L, divided by the gravitational field, 9.8 meters per second. But this equation only really works for small theta. So time period, T, equals 2 pi root L over G. Great, but what does it actually mean? And why? If you've ever done pendulum motion in physics, or you're starting to do it and you're being thrown equations at you, like this one, with no real explanation, then hopefully this video will attempt to fix that, if I do this derivation correctly. So, first of all, we're going to model a pendulum on a plane. So suppose this is a plane. Okay, it's a plane, and I'm going to put a pendulum on it in a location that may seem strange, but this is the way I'm going to derive it. So suppose this is the rope that is attached to a pendulum bob. So that's the pendulum bob. Oops. Okay, and it's a pendulum bob of mass m. So if you remember, F is equal to ma. That's Newton's second law. If it's a pendulum of mass m, we know that the gravitational force that acts on it, given it's reasonably close to the Earth's surface, is mg, where g is the gravitational field strength. So F equals mg. All right, and the way I've drawn this diagram, that force actually acts in this direction. So this vector is mg I hat, where I hat is the unit vector due east. Okay, so hopefully that should make some sense. The length of this string is L. All right, and we also need what I like to call a ticker function, or some sort of oscillator function. So we're going to call this angle theta of t. All right, so it's a special type of function. Actually, we can sort of describe what it does. At different times, it gives us different values of theta. So at t equals 0, we want it to give us some constant value, which is actually the max angle the pendulum can make with what's called a vertical. The vertical in this case is just the x-axis. So maybe that max angle is here, theta max. And at some time t, we want the pendulum here to swing towards this side, actually to negative theta max. So hopefully you should know that an angle that is created when we rotate a ray in the anti-clockwise direction is a positive angle, and an angle that is created when we rotate a ray in the clockwise direction is a negative angle. And so we want this theta of t function to basically take on this value at t equals 0 and then go to negative theta max, and then we want the pendulum to swing back, so we actually want the function to go back to theta max somehow. Now there are many candidates for this oscillator function. Basically, it's any function that does this, that goes from theta max to negative theta max to theta max to negative theta max. Okay, so that's what it is. Well, that's the function we would like to use for the pendulum. Now, I said mg I hat is a force that acts on the pendulum bob of mass m. If it's attached to a string, we also have a tension force. So there's a tension force, I'll call it T hat, that acts on the pendulum. We can actually resolve that force like this. So, oops, we can resolve the force like this. So we have, and force here. I'm sorry if I'm using the same color. Actually, I should change color. So I'll use blue. Okay. Now, this force. Well, what is this force? I'll tell you. It's actually negative t sine theta. From now on, I'm just going to be using theta to mean theta of t. It's just going to take way too long to write theta of t. So negative t sine theta j hat. J hat is simply the vector, the unit vector that points due north. Okay, so that's negative t sine theta j hat, and this vector here, well, this vector here is negative t cosine theta I hat. Okay, so hopefully it should make sense why that's true. Now, what's the position of the pendulum at any given time t? Well, if you're familiar with the polar form of a complex number, we do something quite similar. So the pendulum is really just a point or a vector, whatever you like. The vector is of length L, and so the x component of this vector is simply L cosine theta. Remember, I am saying theta is theta of t, so theta is a function. It's not a constant angle. That's I hat, L of cosine theta I hat. So it has a magnitude of L of cosine theta in the I hat direction, or the x direction, whatever you like, and L sine theta in the j hat direction. So that's its position vector. I'll call it S hat. That's the position vector. I'm just going to rewrite that so it's a bit larger, and actually I think I'll make a new page. Let's see if I can do that. Make a new page. So I'll be constantly referring to this diagram. So maybe you'd like to pause the video and draw it, or create two instances of this video and move the window somewhere so you can refer to this diagram. Alright, so okay. So we said our position vector of our pendulum is L cosine theta I hat plus L sine theta j hat. Okay, and so we can actually work out what our velocity vector is. Well, we just differentiate s with respect to t. So that's just ds dt, and we know that that's nothing but negative L theta dot sine theta I hat plus L theta dot cosine theta j hat. So if you're not sure what I've done there, I've differentiated the position vector, or the displacement vector, in relative to the origin with respect to t, and I've therefore got my velocity vector. The theta dot is just a way of writing d theta dt. Remember, theta is a function of t. It's not a constant angle. It's a function of t. So theta dot is just this. And the way we've got this, well, really all we've done is use the chain rule. So remember, we have, when we're differentiating L cosine theta, theta is a function of t. So by the chain rule, we've got to differentiate this inside function and this outside function. Okay, so the derivative of the outside function is just negative sine of theta, and the derivative of the inside function, well, that's here, isn't it? That's just times theta dot, and the constant remains outside, right? So hopefully that's made it clear, and that you're okay with the fact that this is the velocity vector. And so what's the acceleration vector? Well, the acceleration vector, a hat, well, we just differentiate the velocity vector with respect to time. So that's d v hat over dt. And now things are going to get a bit messy, and it might take a while for me to write everything out. So if you know how to use the product rule, you're very familiar with how to use the product rule and the chain rule. You can just skip ahead and carry on watching from there. So we're going to differentiate v with respect to t, and we're going to use the product rule because we have two functions, u and v. So u is well, we'll say that's theta dot, and v is, well, that's either sine theta or cosine theta. We're going to be differentiating both the x component of this vector and the y component of this vector. Okay, so we're going to be applying the product rule. And I'm not going to spend too long on this. I'm just going to write out what the acceleration vector is. All I'm doing is I'm applying the product rule and the chain rule, right? So let's do it. For the x component, that's negative L theta double dot. Theta double dot is just another way of writing the second derivative of theta with respect to time. So that's just this. Okay, so that's just this. Again, theta is theta of t. Okay, so negative L theta double dot sine theta minus negative L theta dot squared, we're using the chain rule here, squared cosine theta I hat plus, plus, I'm going to do something very similar, same thing, L theta double dot negative sine theta, oh, whoops, no negative sine theta, sorry, L theta double dot cosine theta minus L theta dot squared sine theta j hat. So that's our acceleration vector. Okay, that was this looks like quite a lot of messy algebra, but you'll see it simplifies to something a lot nicer in a while. Okay, so now we're going to refer back to that diagram, and remember how I said if this is my pendulum, so if this is my pendulum bob of mass m, it has a force vector here, which is just m g I hat. All right. There's also, well, if this is the vertical, and this is theta. Again, theta is theta of t. It's a function of time. This is theta. Then this is my tension vector. Right. This is my tension vector. And so I can resolve two other vectors, which, when added together, add up to my tension force. Okay, so the force that acts in the negative j hat direction, well, that's t sine theta, or rather negative t sine theta, j hat. And this vector, well, that's this vector here. This vector here, well, that's negative t cosine theta I hat. So what's the actual force vector that acts on my pendulum bob? Well, I've resolved all the forces on my pendulum bob in the I hat direction and the j hat direction, and so I can just really add all of these together. I can just take the sum of all the force vectors. Okay, take the sum of all the force vectors, and what is that? Well,